Hey AP Calculus students, welcome back. Good news, this is the last lesson for AP Calculus. We're almost there. We're continuing with 8.5. We're applying our integrals and anti-differentiation stuff to science and statistics types things. So before we begin, Hooke's law is something that you might learn in physics. It's pretty easy. So it's something that's applied to springs, So the force is equal to the constant, whatever the constant is, times the distance pulled or compressed. So the first problem is really easy once we understand how to set it up and how it works. So it says a spring has a neutral length of 5 inches. So we have this spring, and at rest, if we're not pulling on it or pushing it, it's 5 inches long. And it says a 200-pound force stretches it to 7 inches. So number one, it's saying find the force constant. So let's set this up. We know the force is equal to 200 pounds, right? 200 pounds is equal to, we don't know what the constant is. It's asking us to find the force constant. But we do know that the distance pulled is the distance between 5 inches and 2 inches. So that's a total of 2 inches total. So here we know that our K is equal to 100. So pretty easy. It's just pretty basic algebra stuff. So it says, how much would it take to stretch it from 5 inches to 10 inches? All right, so let's go back here. So we know that from 5 inches to 10 inches, that would be 5 inches. So we know the constant is 100. We're stretching it 5 inches. So 5 times 100 would be equal to 500. Whatever our thing is. I think it's in newtons, joules. I'm not sure. Whatever the label is for that. Oh, pounds, sorry. Obviously, because we're talking about weight, right? In this case. And we're doing it in pounds. Okay, and then the last one says, how far will it stretch with 1,000 pounds of force? So our force is 1,000. Our constant is 100. And then x is the distance. So this one would be 10 inches. So just good practice, not super duper complicated, but good that we go over it. Now the next one is one that you probably will see on your test or in some capacity. We're talking about pumping and work done from pumping liquid. And this one involves a conical tank. So notice that we have a cone-shaped tank that's inverted, so the point is going downwards. It's filled to within 2 feet of the top with olive oil, and the olive oil weighs 57 pounds per cubic feet. So they're not giving us the total weight of all the oil that's in the can. They're giving us per cubic feet what it weighs. So it's asking us how much work to pump the oil from the tank. Okay, so we have a diagram here. Notice that this red line, we have 2 equations for it. We have y equals 2x or x equals y over 2. We also have 10 minus y, right, is the height of our, represents the height of our oil. And we also show that the tank is 10 feet high, but the oil is only up to the 8-foot mark to start with. So we're trying to pump it all the way down to the bottom. Okay, so for this one, because we have a conical shaped tank and we're working with volume, it'd probably be easier for us to do this by integrating with respect to y, because we have circles that are stacked up on top of each other vertically, right? So if we have things stacked vertically, then it's probably easier if we do this with respect to y. Okay, so the trick though is when we're doing integration with respect to y, we gotta set this up so that everything is set up with respect to y as well. Okay, so we know that the volume is equal to pi r squared times h for our cone. And we need to make sure that we integrate. We're going to use this height of our liquid to find how much work it takes at that given height. So this thing right here is going to be important. So let's go ahead and set this up. So we're going to do the integral from, remember, we're going from 8 to 0 or 0 to 8 here. And then we're going to do pi times the radius, right? So the radius in terms of our y, we can use this form here. So we're going to say that the radius is going to be y over 2 squared, because that's what our radius is going to be at any point from the top to the bottom. It's going to reflect the distance from the middle of the cone to the edge, and we're going to use the equation y equals y over 2, or x equals y over 2, to represent our radius. The second part is our h. So our height, we said, was 10 minus y. And we're doing dy here. And we also know that it's times 57, so let's do that part too. So actually, let's erase this part and put the 57 in there. So we know it's going to take 57 joules or pounds per cubic feet. So 57 here. Okay, now let's start kind of cleaning this up a little bit. So we have probably going to run out of room, but we can bring the 57 pi out here. Y squared, y over 2 squared is going to be y over 4. Y squared over 4, and then 10 minus y dy. We can also bring out this divided by 4, so let's put that outside, so we just have y squared. Okay, and then we can multiply this out, so we have 10y squared minus y cubed dy from 0 to 8. And then we have this 57 pi over 4 on the outside. Okay, let's change colors here. We can probably fit this in here. We're going to move it to the left-hand side. So let's do the integral. So we're going to have 10 thirds y cubed minus y to the 4 over 4. From 0 to 8, and we're not going to forget this in front, so 57 pi over 4. In fact, you might have been able to just do it in your calculator from this point once we set it up, but let's go ahead and do it. The nice thing is when we plug in 0, we're not going to have to do it because this is going to be 0 and this is going to be 0, so let's just calculate the 8. So we have, let's do this calculator part. 10 thirds times 8 to the third, okay, and then minus 8 to the 4th divided by 4, okay, and then times 57 pi divided by 4. and we get 30561. 30561. And that would be in feet pounds. Feet pounds? Feet pounds of force. Okay, so let's kind of go back and talk about this. We started off with our cone. We knew that it wasn't all the way full, so we said that 10 minus y part was going to represent the height of our liquid. Okay, we also knew that the cone wasn't filled all the way up, so then our integral was from 8 to 0 because we knew the original height of the water was 8 feet deep, right? And then we said because we're stacking these up vertically, right, these circles, since we're finding a volume, we're going to do it with respect to y, and that just made things a lot easier. Keep in mind, you could have done this with respect to x and done your shells instead, right? We'd have our cylinders stacked around, making our cone shape. You could have done it. It'd probably be a little bit harder though, because then we'd have to do it that way. But we decided to do it with respect to y because we're just stacking simple circles on top of each other. Then we said, okay, we know that the volume is equal to the pi r squared times h. That's the volume for our cone. So what we did there, then we said that, okay, let's go ahead and figure what this looks like. So we have this y over 2 from our line that represents the outside of our cone. So we're going to use that because it's in terms of y. We also said the height was 10 minus y from the beginning, right? So this represents our volume. We also had to add in this 57 because the 57 is the amount of pounds we have to push or have to pump per cubic meter. Okay, so then we started simplifying some stuff, made it a little bit easier on ourselves, and then we did our integral. Keep in mind that at this point here, or actually at this point here, we could just plugged it into our calculator and been done with it. But the tricky part about these pumping things is we have to make sure that we represent our volumes correctly and we integrate with respect to the correct variable. All right, so good job today. It's been a pleasure being your teacher. I'm going to miss you guys when you're gone, and I hope you do your absolute best and score well on your end of course exam. Good job.